Thevenin's theorem. Finding the output attributes of a circuit, output voltage and resistance, to make modular units easier to match up to each other. This tutorial will make use of voltage dividers throughout. Okay, we've got a black box, and we may not know what's inside this module, but we can still determine the voltage across the ports A and B, and we can work out its output resistance. We do that like so. First of all, we'll measure the voltage across the ports A, B with a voltmeter. Next, we'll short the port A to ground, so we'll bring that to ground and take it through an ammeter here, like so, and record the current. So here we've connected the A and right back to B with an ammeter in the middle to record the current. And then finally, with the voltage found with the voltmeter and the current known with the ammeter, we can find the resistance simply by using Ohm's law, which will be the voltage we measured divided by the short circuit current. So then we've got, for this module, we've got the output resistance and we've got the output voltage. Commonly the output voltage is named VTH, named after Thevenin, and this output resistance can be called RTH, but that's generally only use those names when we're doing the circuit analysis with actual calculations. Here it's not strictly necessary to use RTH and VTH, because what we've done here is what's called the brute force method of actually using the instruments on a black box to actually get the output voltage and the output resistance. So finally, once we've got the output resistance and the output voltage, then we can redraw our module here in a diagram form. We can emulate it as this circuit here. So this circuit here is the voltage measured and includes the resistance, the output resistance. Now we can now calculate for any load resistance we put onto this module. We can calculate now that we've done this brute force method of measurement. We can now just easily use a voltage divider to calculate many different load resistances. But for most modules we see in electronics, we will know the circuit analysis beforehand anyway. So in that case there's a more elegant method than using this brute force method. But I wanted to show you this because the logic here is more or less the same as the way you'd calculate it, and in the lab I'll do one of these. I'll actually do the brute force method to show how that that's relevant. So let's look at the analysis method of doing this. So in this case, you would I've chosen a circuit here which is two resistors in series using a voltage source. The reason I've chosen that is a very, very common layout. It's a very common circuit and it's used in lots of different scenarios, so it's a very useful one to actually show Thevenin's theorem. So first of all, as in the brute force method, we're going to measure the voltage, but this time we're going to do it, we're going to calculate it given we know that the components in this circuit. So to find the output voltage, which we call the Thevenin voltage, all we have to do is find the voltage that's dropped across AB, because we've placed the port AB across the resistor R2. So what we want to do here now is find the voltage here, which we call the Thevenin voltage, and that is just a voltage divider, as you can see. So it's the proportion of the voltage that's dropped across R2 against the whole of the resistance here. So that's basically R2 divided by the total resistance times the voltage source. So that gives us the Thevenin voltage. So we have that now. So in step 2, what we'll want to do is to find the short circuit current. Now what we do here is we take we short A to ground, which is what we did in the brute force method, but we're going to calculate it here in this way. So if we short A to ground here, obviously we got the R1 here to calculate. So here we can find the short circuit current is simply the voltage source divided by R1. So now we've got the short circuit current. Now to find the Thevenin resistance, all we need to do is divide the output voltage by the short circuit current, and that will give us the output resistance, or the Thevenin resistance. So that's what we do. We're going to take the one, in this case it's 1 over the short circuit current, which is the same as saying Ohm's law, voltage over current. Yeah. So I've just written it out like this so that you can see the equivalence here. So 1 over IS is simply RI over VS. So I've written that here. So that's then, of course, the Thevenin voltage is the voltage divider calculation we did. So we place that there, and you can see here that the two voltage sources cancel, and we're left with a really neat solution. We're left with the fact that for this series resistance, whether you've dropped the voltage across the bottom resistor, you're left with a really nice result. Basically, R1, R2, after you've cancelled the voltages, you're left with R1, R2 divided by the total resistance, which is the same as calculating a parallel resistance equation here. So with that in mind, finding the Thevenin resistance is no different from assuming that the voltage source is 0 and treating R1 and R2 in parallel, looking into the port. So if ever you get a circuit such as this, which you often will, then you just remember that you're just calculating the parallel resistance. In fact, there's a rule for all for calculating the Thevenin resistance, and that's always to short the voltage sources and open any current sources. So that's the only thing you really need to remember about Thevenin, is you short. In other words, you set VS to 0, you short it, and you open any current sources, and then you can work out the Thevenin resistance for any circuit. So in this particular case, it's the parallel resistance R1, R2 if you've dropped your voltage across R2. So in steps, basically what you do is you calculate the Thevenin voltage, as we did, then you find the short circuit current, and then with the short circuit current you're able to find the Thevenin resistance. And once you've got those, once you've got the Thevenin resistance and you've got the Thevenin voltage, then you can simply redraw this circuit as this. So finally we can redraw the circuit as a Thevenin equivalent circuit. So you've got the Thevenin voltage, the Thevenin resistance, the A and B ports, and any load resistance you want to place there. So for any load resistance, we now just have a simple voltage divider to calculate. So that's basically how you calculate it. Okay, here's just an example. So here we've got a circuit, and where the question we're given is calculate the voltage across the load resistor RL and the current through it when RL equals 30k, 10k and 5k. So because of this, what we could do is, first step is convert beyond the ports here, convert this area here into Thevenin equivalent before we actually work out the 3 versions for the RL. Be much easier this way. So first step then is to get this circuit converted to its Thevenin equivalent, like so. So we're going to remove the load resistor. Then we're going to find the Thevenin voltage, which is the proportion here. So it's 20 over 30 times 6. So we've got 20 over 30 times 6 volt. So the Thevenin voltage is 4 volt. Very easy. So we've got this voltage drop across here. The Thevenin resistance is the parallel resistance looking in, ignoring the, so we're looking in here, it's 10 in parallel 20, so that comes out to be 6.67 kilo ohms. So now we can redraw this into the equivalent Thevenin circuit, which is here. So we've got the 4 volts that we found across here, and the Thevenin resistance is 6.67 kilo ohms. So now all three load resistor voltages and currents can now be found as follows. So we start with the 30. So let's say there's R30, where if we put RL30 here, again we've got a very simple voltage divider here. So it's RL divided by RTH add RL. So that gives us times the voltage. So we got we've got here for the voltage across the load will be, like I say, RL over RTH at RL times 4 volts. So it's 30 over 6.7 add 30 times 4 equals 3.27 volts. And for the current that runs through it, well, obviously that's just VTH, and there's total resistance is RTH at RL, so that's just VTH divided by the total resistance. So that gives us the short circuit current, which is 0.1 milliamps. So we found both the current and the voltage for 30k, and the same for R10. We do exactly the same process. I won't go through it all again. So it's just simply IL equals, using these same values again, comes to 0.23 milliamps, and for 10 it comes to 2.399 volts. You can see we haven't had to go through any analysis now. All we've done is just used these results, these two equations. So now we could use as many loads as we want. So we've done the 5k one as well. We just use these two equations again, and we've got 0.34 milliamps and 1.71 volts. So the point of this is, if you was to do this by actually the old, if you didn't use the Thevenin voltage, you'd have to calculate the parallel resistance here, and then find the current through it, and then find the current through this one to get the voltage drop across this one. So it would take much longer, and this is quite a simple circuit. I mean, if you had more components and things going on here, it would initially take a while to get your initial Thevenin voltage and Thevenin resistance, but once you'd got them for multiple loads, it would be as quick as just using these two equations. So that's why Thevenin's theorem is really useful. The other reason it's really useful is the fact that it's great for matching up modules. So if you've built one module, you'll know, for example, if you've got your module and you've worked out your Thevenin resistance and your Thevenin voltage, then you've just got two attributes of that module, which allows you to match it up to other modules. So you can match this up to an input module where you want to sort of balance the loads. You want to make sure that the resistance here is a lot lower than the one you're attaching it to, so most of the energy and most of the voltage can drop across the new module. So with this information, you've got, like, you can have many modules with just the two attributes, Thevenin resistance and the Thevenin voltage. So if you like, the output voltage and the output resistance enables you to have modular circuits, so you can build nice modules. So that's really the great thing about Thevenins. Okay, on the next tutorial I'm going to move on to capacitors, and we're going to see this voltage divider more often with capacitors when we start looking into filters, etc., which gets a lot more interesting. Okay, thanks very much.